All right, so enough of that. Let's get started with the actual organic chemistry. So, this first question is, what happens to a molecule during a reaction? And it's a very complicated question because there are a ton of possible answers here. So the first thing could be a collision, right? And in the course of a reaction, you have to have two molecules come together. They have to come together, otherwise you're not going to get a reaction to occur. At least in most reactions, you need two molecules to come together in order to get a change to occur, a transformation to occur between those two molecules. And when they come together, a bond has to make or be made or be broken, right? So bonds are breaking or forming. And the question is, what is a bond? And the short answer to this is a bond is a shared pair of electrons, and we're going to talk about that throughout the course of this chapter and throughout the whole semester. A bond is a pair of electrons. We'll come back to that. And making and breaking bonds is what's important in organic chemistry. All right, so the big question is, why do reactions occur? And we're going to come back to this over and over again. This will be the focus of 2 chapters of organic chemistry, right? So there's a lot going on that we're going to see, we're going to do to answer this question right here. Focus on the electrons, right? Bonds are electrons, and that means that if we want to answer this question, we need to focus on the electrons. So electrons are where we're going to try to focus throughout the course of the course. All right, so here's an example of a critical skill, an acid-base mechanism, and we're gonna start with this now. And normally, if I were teaching this class in person, I would say, take 5 minutes, right? Think about this question. You might know the answer to this question from your previous chemistry knowledge, right? From Gen Chem. Take 5 minutes to try to answer this question. Since we're doing this online, right, and this is video, I'm not going to do that. We're going to walk right through it right now. So you might recognize HCl as a strong acid, which is H plus and Cl minus, right? And they're ionic bonds, right? An ionic bond is a bond between two different ions, right? Opposite charges attract. And sodium hydroxide, Na plus and OH minus. And you might notice that OH minus and H plus can go together to create H2O, and Na plus and Cl minus can go together to create NaCl. So that's the answer to this question. But it's not so simple. In order to get there, you would have had to have memorized that probably from your general chemistry knowledge. We can answer this question in a more logical way than just saying, yeah, we know that a strong acid and a strong base like HCl and NaOH will go together to create water and sodium chloride. And if this didn't make any sense to you and you didn't recognize it, that's okay. We haven't done any organic chemistry yet. I'm not expecting you to know this reaction yet. Next chapter is going to be acid-base chemistry. I think chapter 3 is actually acid-base chemistry, and we're going to spend a lot of time on this sort of thing. But this is a good example reaction, which is going to help us to go ahead and work through this sort of electron question, this bond question. Because what we're doing in this question is we're creating a new bond between the hydroxide and the H+. So we're going from H+ and OH-, and I'm drawing some Lewis structures here, so I'm showing valence electrons, to HOH, H2O. What that's doing is it's creating a new bond between the hydrogen and the oxygen. So we can talk about this in terms of electrons moving from being on the oxygen. There's an excess of electrons on the oxygen, hence it has the negative charge, and there's a lack of electrons on the hydrogen, hence it has the positive charge. And we're taking those two species and combining them, and the electrons, the excess of electrons on the oxygen, are moving into a new bond between the oxygen and the hydrogen. So in order to understand this reaction, we're going to need to talk about bonds, right? We're going to spend a lot of time talking about bonds, but let's jump into that right now, and we'll get some ideas as to what we're doing, what we're talking about. All right, so here's some very basic review. Right, atoms are made up of protons, neutrons, and electrons. The nucleus contains positively charged protons, right, and neutral charged neutrons, right? So neutrons have no charge, and the nucleus is overall positively charged. Therefore, protons and neutrons have nearly the same mass. They're almost 1,800 times the mass of an electron. And therefore, most of an atom's mass is packed up in the nucleus. Electrons are negatively charged. And the electrons are outside of the nucleus. The nucleus is where the protons and the neutrons are. It's a small space in the middle of an atom, and outside is this sort of electron cloud, right? And I have it called here an electron cloud. And I really like that definition, or that description of the electrons. They really are sort of like a cloud around the outside of the nucleus. And that's where bonding takes place, right? It's not bonds between two nuclei that occurs. Those are nuclear reactions. They do happen, but that's just beyond the purview of organic chemistry. That's not what we talk about. Bonding for us is going to take place in the electron clouds. So those electron clouds where the electrons are is where this is important. So this is why we're focusing on electrons when it comes to creating bonds. All right, so a little review for isotopes. Remember, isotopes are different forms of elements where there are more or less neutrons. So they have the same number of protons, but a different number of neutrons. So if you look at something like oxygen, the normal isotope for oxygen is O16. Right, and this is this number in the upper left-hand corner representing the isotope. That number tells you the atomic mass of the isotope. So for O16, it's 16, indicating that because it's oxygen, it has 8 protons. That never changes. Oxygen always has 8 protons, right? That's the atomic number right here. Oxygen always has 8 protons. But if you add a neutron or two, you get into O17 or O18, right? And those have an increased mass number, but the same charge around the nucleus. So isotopes represent elements or atoms where the mass has increased by 1 unit, right? 1 or 2 neutrons, or has increased by a certain number of neutrons. But the charge stays the same. The nuclear charge stays the same. It's always 8 protons in an oxygen nucleus every time. Atoms with the same number of protons, different number of neutrons. Mass number is the sum of the protons and neutrons. And that's that 16, 17, or 18. And here I have, in this case, right, 99.762% of oxygen that's naturally occurring is O16. So, and that's typical. Usually there's one big mass, one large mass that you see, one large isotope that occurs the most frequently. In the lower elements, it's usually the one with the same number of protons and neutrons, but not always, so we'll be paying attention to that. All right, so if you recall back to your Gen Chem, right, here's a few words that you may recall. Atomic number, that's the number of protons in the nucleus. Remember, for oxygen, it was 8. That always stays the same for oxygen. For carbon, it's always 6. For nitrogen, it's always 7. And for oxygen, it's always 8. The mass number is the sum of the protons and the neutrons, right? That will change for different isotopes. Isotopes have the same atomic number, but different mass numbers. Atomic weight is the average, right, of all of the naturally occurring elements. So this becomes important. So atomic weight is something we need to take a moment to describe here. Because when you see a weight of an atom or a weight of an element reported, it's typically the atomic weight, which is the weighted average of all of the naturally occurring isotopes. So if O16 is the most abundant, what do I mean by weighted average? I mean that you take the average of the elements, but you weight it towards the one that's the most abundant. So if O16 is 99 point whatever percent most abundant, we'd say 99% of that average is composed of O16, so it's going to be really, really close to 16. So you'll see that the weight of oxygen is usually listed as, that's 15.99, isn't it? There's some other things going on there. But the atomic weights are not always like 16 even, right? They're not the mass number. They're not 16 for oxygen. They're a little bit different. And the reason for that is because you're taking a weighted average of the isotopes. So you're gonna need to pay attention to that. When you combine a bunch of atoms together and you make a molecule, the molecular weight is going to be the sum of the atomic weights. That includes the averaging that goes on with the naturally occurring elements, or isotopes, I should say. So molecular weight is going to be the sum of all those atomic weights in a molecule. All right, and this last question down here at the bottom is, what are the isotopes of hydrogen? And this is going to be important. We're going to see this show up a few times. Oh, I don't have a slide for this. So the isotopes of hydrogen that you're going to see frequently are going to be H1, which is hydrogen, H2, which is deuterium, and H3, which is tritium. They all have one proton in the nucleus. H1 has no neutrons, and this is the most abundant isotope of hydrogen. So this is the one that we most commonly talk about. H1 has no neutrons, and I do my best to say that a hydrogen atom is a hydrogen atom, but frequently I call it a proton. And the reason I call it a proton, and I will slip up and I will do this all day long, I will call hydrogen atoms protons. The reason I call them a proton is because hydrogen atoms, especially if they don't have any electrons, are composed of just a proton. There's no neutrons, right? That atomic mass number, right, is telling you that there's no neutrons. The atomic weight of 1, right, no neutrons, just one proton in the nucleus. And therefore, if you have no electrons either, all you have to make up that atom is a proton. So anytime I'm talking about an H plus atom, I will be talking about a proton. And frequently when I'm talking about hydrogens on a molecule, I will say that proton there or this proton here. And the reason why is because hydrogen atoms are essentially just composed of a proton. So my apologies if I slip up and say proton all the time, which I will. I will try to say hydrogen atoms, but I'm not so good at that. All right, so if you look at a periodic table, typically you'll be given this much information in a periodic table. An atomic number will frequently be on top. You'll get an element symbol. That's usually the first letter of the name. Sometimes not. Sometimes the first letter of the name, they use the first letter of the Latin name for the element. So it's different, right? So for lead, it's Pb, which stands for plumbum, which is not our name for lead, right? So you see them, they're different, but they do have some correlation to reality. Usually it's a Latin name as opposed to an English name or a name that you would recognize. You'll also be given typically atomic weights, right? And that atomic weight, remember, is the sum of the isotope averages, right? So take that into account. And then the element name is usually given to you in a periodic table as well. All right, so moving on from atoms, we're going to move on to just a hair of electron configuration material. And this is going to be important because this is going to play a role in bonding. So a few things that we need to talk about with regards to electron configurations. When you remember, as you go through that periodic table, everything is aligned such that at the very right side of the periodic table, all the way over to the right side of the periodic table, those atoms in their neutral state have a completely filled valence shell, or a completely full shell of electrons. So as you start on the left, you have 1 electron, and then you go to the next element, it has 2 electrons, and then you go to the next element, it has 3 electrons in that last shell. And finally, when you get all the way over to the right, you have a completely filled shell of electrons. And that filled shell of electrons is especially stable. So if you remember, right, a lot of times we'll refer to an atom, right, there's a nucleus of an atom, right? Here's the 1 shell, here's the 2 shell, here's the 3 shell, and there's subshells, and we'll talk about those in a little bit. But anytime you add an electron, you're going to put it into the lowest energy shell that has an open spot for it, or vacancy for it. And as you fill a shell completely, but don't jump into the next shell, then you hit some extra stability, an extra stability situation. So atoms will do what they can to get to that stable situation where they have a full shell, not more or less than a full shell. So if an atom has too many electrons, it might give one up pretty easily to get down to a full shell. If an atom has too few electrons, it might take one pretty easily to get up to a full shell. They like to have full shells. It makes them stable, it makes them happy. So a filled shell of an electron is the electron configuration of a noble gas, such as, let's say, for example, argon, or actually, let's say neon. Neon, right? Neon's a noble gas, and if you look all the way over to the right of the periodic table, you'll see neon. Neon's a noble gas, and it has a completely filled number 2 shell, and that makes it very stable. So the atoms that are, let's say, to the left of neon are going to prefer to add electrons to get up to neon's electron configuration. And the atoms that are down on the next row, all the way over on the left of the periodic table, are going to prefer to drop an electron to get back to neon's electron configuration. This principle has come to be called the octet rule, because a filled shell implies 8 valence electrons. So as you look at your first 3 rows of the periodic table, if we ignore the first row, the next 2 rows each have 8 elements in them, and that's because it takes 8 electrons to fill the second shell and the third shell. And if you, well, we'll talk about the third shell later, but it takes 8 electrons to fill that second shell. And that's the group of atoms that we're going to be concerned with the most. Anyways, that's where carbon is. It's in that second row of the periodic table. So anytime you can put 8 electrons around that shell, in that second shell of an element, it's going to be a very special situation. That 8 valence electrons is called the octet rule. And the octet rule is just saying get 8 electrons in the valence shell.